Hi, this video is a 10-minute introduction into the basics of robust statistics. We will start by looking at estimating the location and correlation parameters to see how robust estimators behave relative to their classical non-robust counterparts. I will then discuss some aspects of my own research in estimating a sparse precision matrix in the presence of Cellwise contamination. At the end are some references you can use to find out more about the various techniques presented. So, let's get started. The aim of robust statistics is to develop estimators that model the bulk of the data and are not unduly influenced by outlying observations or observations that are not representative of the true underlying data generating process. To explore this idea, we'll consider the simple case of location estimation. We'll look at three estimators: the mean, the median, and the Hodges-Lehmann estimator of location, which is just the median of the pairwise means. In this example, we have 10 observations drawn from a uniform distribution over the range 0 to 10. All three estimates of location start off close to the true parameter value, which is 5 in this case, but what we'll do is observe how they behave when we artificially corrupt some of the observations. We start by taking the largest observation and moving it to the right. When we do this, the mean also starts to increase, which is what you would expect from a non-robust estimator. In contrast, the Hodges-Lehmann estimate and the median remain unchanged. It is this resilience to contamination that makes them what we call robust estimators. If we take the two largest observations and move them to the right, the median stays the same. The Hodges-Lehmann estimate jumps from 5 to 5.5 but then stays constant, and the mean reacts as before by increasing as the contaminated observations increase. We observe similar behavior when the three largest observations are contaminated. When the four largest observations are contaminated, the Hodges-Lehmann estimate now behaves just like the mean in that both estimators are in breakdown. That is to say, they are no longer representative of the bulk of the data. And when 5 observations are contaminated, even the median is no longer sure which observations represent the original data and which are the contaminated observations. So it also returns an estimate that is no longer representative of the location parameter of the original data generating process. We can observe similar behavior in multivariate datasets. In this example, we're looking to estimate the correlation between variables. In the lower half of the matrix, we have scatterplots of 30 observations. For example, this scatterplot shows variable 2 on the y-axis and variable 1 on the x-axis, whereas this one has variable 2 on the x-axis and variable 3 on the y-axis. In the upper half of the matrix, we have the true parameter values that I used to generate the data, the classical correlation estimates, and the robust correlation estimates between each of the pairs of variables. The robust estimator that I've used is the minimum covariance determinant estimator, and you can find links to further details at the end of the presentation. We're going to observe what happens to our estimates when we take 3 observations and move them away from the main data cloud. Let's focus on the relationship between variable 1 and variable 2. As the observations move further away from the data cloud, the classical correlation estimator is decreasing and eventually it becomes 0, suggesting that there is no correlation between variable 1 and variable 2. As the contamination moves further away, the classical estimate is now giving a negative value, suggesting a negative relationship between variable 1 and variable 2. In contrast, the robust estimates have all stayed reasonably close to the true parameter values as they are modeling the core of the data and are not as influenced by these outlying values. Let's look at a real example. Some work I do for the industry body Meat and Livestock Australia is concerned with predicting the eating quality of beef. They run a large number of consumer tests where consumers are asked to rate pieces of meat on their tenderness, juiciness, flavour, and give an overall score. The aim is to develop a predictive model that rates each cut of meat as 3, 4, or 5 star based on what we know about consumer preferences. Here's a scatter plot of ratings for almost 3,000 pieces of meat. There's obvious structure in the dataset, with tenderness, juiciness, flavour, and overall being highly positively related. However, there's also a lot of noise, with some consumers giving very high scores for some variables and low scores for other variables. For example, up here, you've got some observations where consumers have given very high tenderness scores, but very low overall scores. If you calculate classical covariances, you can see that there is a reasonably strong positively linear relationship between the variables. However, robust techniques such as the minimum covariance determinant can be used to highlight the tightest core of the data, which represents the relationship between the variables for the majority of consumers, which suggests that the true underlying correlations between variables are much stronger than the classical method would otherwise suggest. For example, the relationship between flavor and overall goes from 0.86 up to 0.99 when you restrict attention to the tightest half of the data. Something that I've looked at in my research is estimation in the presence of cell-wise contamination. Traditional robust techniques, such as the minimum covariance determinant we used earlier, assume that contamination happens within the rows of a dataset. Furthermore, even the most robust estimators can only cope with at most 50% of the rows being contaminated before they no longer work effectively, as we saw earlier with the median breaking down when there were 5 contaminated and 5 uncontaminated observations. This assumption of row-wise contamination may not be appropriate for large datasets. What we have here is a heat map of a data matrix. The white rectangles represent corrupted cells. In this situation, with a small amount of cell-wise corruption that affects less than half of the rows, classical robust methods will still perform adequately. However, as the proportion of scatter contamination increases, or the contamination is allowed to spread over all the rows, then you might end up in a situation where all observations have at least one variable that is contaminated. There's still a lot of good data in this dataset. The challenge is extracting information about the core of the data without your estimates being overwhelmed by the contaminating cells. In particular, I've looked at estimating precision matrices in the presence of cell-wise contamination. A precision matrix is just the inverse of a covariance matrix. However, often in large datasets you also want to assume that the precision matrix is sparse. That is, there are a number of zero elements in the precision matrix. This is particularly useful when modeling Gaussian Markov random fields, where the zeros correspond to conditional independence between the variables. We'll briefly apply these ideas to a real dataset to finish off. We have 452 stocks, or shares, over 1,258 trading days. We'll observe the closing price, which we convert to a daily return series, and we want to estimate a sparse precision matrix to identify clusters of stocks. That is, groups of stocks that behave similarly. To do this, we used a robust covariance matrix as an input to the graphical lasso, details of which can be found in the references at the end of the presentation. If we look at the return series for the first 6 stocks in the dataset, we can see that there are a number of unusual observations scattered throughout the data. For example, you have this negative return for 3M Co, again for Adobe, and AMD also has a number of unusual observations. This suggests that perhaps there is a need for robust estimators when analyzing this dataset. We're going to visualize the results as a network of stocks. If there is a non-zero entry in the estimated precision matrix between 2 stocks, then they will both appear in the graph with a line linking them. Furthermore, I've colored the stocks by industry. We can see here in the classical approach that we have some clusters of stocks. However, if we use the robust approach, these clusters are much more densely populated. So it's identified linkages between more stocks than the classical approach did, reflecting the fact that the robust method is not as influenced by those unusual outlying observations. So we've got a financials cluster over here, we've got an information technology cluster down here, a utilities cluster, and an energy cluster. If we add some additional contamination, the classical approach is no longer able to identify those clusters of stocks. It gives you just this soup of linkages with no clear structure. The robust approach, on the other hand, gives you essentially the same as what we had before when I didn't add the extra contamination in. So you've still got information technology clusters, you've still got an utilities cluster over here, and a financials cluster down there. So what this tells you is that the robust methods are modeling the core of the data and are relatively unaffected by unusual or extreme observations. So that's been an extremely brief introduction into the idea of robust statistics. The take-home message is that the robust methods are designed to model the core of the data without being unduly influenced by outlying observations that are not representative of the true data generating process. If you'd like to know more about any of the methods presented here, you can check out these links for the Hodges-Lehmann estimator, the minimum covariance determinant, this is a nice recent review paper, or the graphical lasso. Here's some of my work, and there's a paper that's to appear in Computational Statistics and Data Analysis on the robust estimation of precision matrices in Cellwise contamination. To understand that, it would perhaps help to go back to an earlier paper on robust scale estimation, or you could check out my PhD thesis, which is available at that link there. If you'd like to get in touch, there are my details, and you can find a copy of these slides at this link.